Hello, and welcome to Sleepy Engineering. In this video, we will explore the complete history, design, and function of one of the largest and most impressive structures in modern engineering, the oil platform. This narration is intentionally slow, detailed, and repetitive. It is designed to help you relax, focus, or fall asleep. There will be no sudden sounds, no music, and no emotional tone. Only the steady voice of information. Now please sit back, close your eyes if you like, and let the story of the oil platform begin. Oil platforms are among the most significant structures in the field of modern engineering because they enable the extraction of resources that fuel the global economy and shape the daily lives of billions of people around the world. And to understand their role, it is important to begin with a simple definition. For an oil platform is a large offshore structure built to support drilling operations, extraction systems, storage equipment, and living quarters for workers who spend weeks or even months at sea. The purpose of these platforms is to access reservoirs of crude oil and natural gas that lie beneath the seabed, sometimes in shallow waters close to the coastline, but often in deep or even ultra-deep water regions, where the challenges of engineering, logistics, and safety reach remarkable levels of complexity. The significance of oil platforms lies not only in their size or their technical sophistication, but also in their contribution to the global energy supply, because petroleum remains one of the most important energy sources in the modern world, used to power vehicles, generate electricity, produce heat, and serve as the raw material for countless products such as plastics, chemicals, and fertilizers. Without oil platforms, the offshore portion of petroleum production would be impossible to achieve. And since offshore reserves account for a large percentage of global oil output, these structures have become indispensable. Oil platforms are more than simple machines. They are floating or fixed cities in the sea, combining elements of civil engineering, mechanical engineering, electrical systems, and human organization, all working together to achieve the steady extraction of hydrocarbons. They represent an intersection between technology and environment because they are built in locations that are inherently hostile, with high winds, strong waves, saltwater corrosion, and unpredictable weather events that constantly test the strength of materials and the precision of design. From an economic perspective, oil platforms are vital because they ensure access to reserves that would otherwise remain unreachable, and they allow nations and companies to secure energy supplies, create jobs, and sustain industrial development. From a geopolitical perspective, they play a role in energy security, trade relations, and sometimes even international conflicts, because the control of offshore fields can influence political decisions and alliances. From an environmental perspective, they raise questions about sustainability, ecological risks, and the balance between human needs and natural systems, because accidents, spills, and emissions can have lasting effects on marine life and coastal regions. Oil platforms can be classified in many ways, and in later sections, we will discuss the different types, such as fixed platforms, compliant towers, semi-submersibles, drillships, tension leg platforms, and spar platforms, each of which has unique advantages and is suited to specific water depths and geological conditions. But for now, it is enough to note that their existence has transformed how the world accesses energy beneath the ocean. These structures are feats of engineering, not only because of their size, but because of the logistical effort required to build, transport, and operate them, involving thousands of workers, specialized ships, helicopters, pipelines, and support facilities. To imagine the scale of their importance, one can consider that a single platform may produce hundreds of thousands of barrels of oil per day, and when multiplied across the many hundreds of platforms currently in operation worldwide, the output becomes a central part of the global economy. Oil platforms are also symbols of human ingenuity because they demonstrate the ability to adapt to extreme environments and to design solutions that function reliably under immense pressure and constant strain. Yet at the same time, they remind us of the dependence of modern society on finite resources and the need to consider the future of energy. As we move forward in this video, we will trace the origins of offshore drilling, the evolution of platform types, the challenges of construction, the processes of drilling and extraction, the systems of safety, and the debates around environmental impact and future alternatives. But all of these discussions begin with the recognition that oil platforms are not just machines in the ocean, they are essential pillars of the modern energy system, holding together the supply chains that keep transportation, industry, and households functioning day by day. The history of oil platforms begins with the early attempts to extract oil from beneath bodies of water, long before the sophisticated offshore structures of today existed. And to understand this development, it is necessary to go back to the late 19th and early 20th centuries, when the demand for petroleum was growing rapidly as industrial societies embraced oil as a fuel for lighting, heating, and eventually for internal combustion engines. The very first experiments in offshore drilling were not carried out in deep oceans, but rather in shallow lakes, bays, and coastal waters, where wooden piers were extended into the water to allow drilling equipment to be positioned above potential reservoirs. One of the earliest recorded offshore wells was drilled in 1891 at Summerland, California, where entrepreneurs built piers into the Pacific Ocean and mounted drilling rigs directly onto them, a method that allowed access to oil deposits just beyond the shoreline. These structures were rudimentary compared to the massive steel and concrete platforms of later decades. Yet they represented an important step in the evolution of offshore engineering, because they demonstrated that oil could be successfully extracted from beneath the seabed. As the 20th century progressed, the expansion of the automobile industry and the growth of electricity production created an enormous appetite for petroleum, and companies began to search for new reserves in increasingly challenging environments. By the 1930s and 1940s, oil companies in the United States and other regions were experimenting with barges and artificial islands that could support drilling equipment farther from the coast. These early offshore rigs were still limited to relatively shallow water, often no more than a few dozen feet. But they proved the concept that the sea itself could be a frontier for petroleum exploration. The first true offshore platform that was not connected to the shoreline was built in 1947 in the Gulf of Mexico by the Kerr-McGee Oil Company, Brown and Root, and Phillips Petroleum. Located about 10 miles off the coast of Louisiana, in water roughly 15 feet deep, this platform marked a turning point because it demonstrated the feasibility of constructing a completely self-contained structure at sea, independent of land-based supports. Unlike the wooden piers of Summerland, this platform was built of steel and was designed to withstand the forces of wind and waves, setting a precedent for future offshore engineering. The success of this project sparked rapid interest in offshore drilling across the world, and during the 1950s and 1960s, oil companies expanded into deeper waters and more distant locations. As techniques improved, platforms were built in water depths exceeding 100 feet, then 200 feet, and eventually much deeper, each milestone requiring innovations in materials, structural design, and drilling technology. In many ways, the history of offshore drilling mirrors the history of engineering itself, as each challenge encountered in the field led to the invention of new methods, new equipment, and new approaches to safety and logistics. It is important to recognize that the early offshore industry was driven not only by technical ambition, but also by economic necessity, because the easily accessible oil reserves on land were already being exploited at a rapid pace, and companies knew that the ocean contained vast, untapped resources. The first platforms also highlight the human element of offshore drilling, as workers had to adapt to long stays at sea, often in isolated conditions, relying on boats or helicopters for transport, and living in close quarters on structures surrounded by water. These early pioneers of offshore work laid the foundation for the culture of offshore labor that continues today, characterized by resilience, discipline, and a unique lifestyle shaped by the rhythm of shifts, weather, and machinery. By the end of the 1960s, offshore drilling had established itself as a permanent sector of the petroleum industry, with platforms appearing in the Gulf of Mexico, the North Sea, and other regions known for significant reserves. Each of these developments built directly upon the lessons of the early platforms, from the wooden piers of Summerland to the first freestanding steel structures in the Gulf, and they collectively marked the beginning of a new era in energy production. The history of these first platforms is therefore not only a story of technological progress, but also a story of how necessity, ambition, and experimentation combined to open a new frontier for human industry in the oceans of the world. Fixed platforms are among the earliest and most straightforward forms of offshore structures, and their design reflects the principles of stability, durability, and permanence, because they are constructed to rest directly on the seabed. These platforms are built using large steel or concrete legs that extend from the ocean floor up to the surface, supporting the deck that carries drilling equipment, production facilities, storage systems, and living quarters for workers. The essential idea behind a fixed platform is to create a stable base that can withstand the forces of waves, currents, and wind, while providing a secure foundation for heavy machinery and continuous drilling operations. The legs of a fixed platform are usually secured to the seabed using piles, which are long steel tubes driven deep into the ground to anchor the entire structure. In some cases, gravity-based foundations are used, particularly in areas with suitable seabed conditions, where the massive weight of a concrete structure keeps it firmly in place. Fixed platforms are typically used in relatively shallow waters, usually up to 500 meters in depth, because beyond this limit, the weight and cost of construction become impractical. One of the advantages of fixed platforms is their ability to remain in place for decades, often producing oil and gas continuously for 20 to 30 years before decommissioning or replacement is considered. Their decks can be very large, providing space for drilling rigs, cranes, processing equipment, pipelines, and even helicopter landing pads, making them self-sufficient facilities capable of handling many different aspects of offshore production. The stability of fixed platforms also allows them to operate in harsh environments, such as the North Sea, where strong waves and storms are common, and their robust construction provides a level of safety and reliability that has made them a standard solution for offshore production in shallow and moderate depths. Building a fixed platform is a massive engineering project that begins with extensive geological surveys to determine the suitability of the seabed, followed by the design and fabrication of the legs, jacket structures, and topsides. The jacket, which is the steel frame that supports the platform, is usually built on shore in specialized fabrication yards and then transported by barge to the offshore site. Once in position, the jacket is lowered into the water, aligned carefully and anchored to the seabed with piles driven by hydraulic hammers. After the jacket is secured, the topside modules, which include the drilling equipment, living quarters, and processing facilities, are lifted into place using heavy lift vessels. This assembly process can take months or even years, depending on the size of the platform and the complexity of the operation. Once completed, a fixed platform becomes a semi-permanent structure in the ocean, requiring regular maintenance, inspections, and upgrades to ensure continued safe operation. The economic significance of fixed platforms lies in their reliability and long-term productivity, as they can extract vast amounts of oil and gas from offshore fields and connect directly to pipelines that transport hydrocarbons to onshore refineries and terminals. However, fixed platforms are not without challenges, as their construction is extremely expensive. Their installation requires favorable weather conditions, and their eventual removal or decommissioning presents logistical and environmental difficulties. Despite these challenges, fixed platforms remain an essential part of the offshore industry because they represent a proven solution for stable and efficient production in shallow and mid-depth waters. They are often the first choice when developing offshore fields that are close to shore or located in regions with a history of strong storms, where stability is crucial. As offshore drilling expanded into deeper waters, new types of platforms were developed to address the limitations of fixed designs, but fixed platforms still form the backbone of offshore production in many parts of the world, standing as massive, immovable structures that symbolize the enduring human effort to harness energy from beneath the sea. Compliant towers represent a unique category of offshore oil platforms that combine the stability of fixed platforms with the flexibility needed to operate in deeper waters, and they stand as a transitional solution between shallow water structures and the fully floating systems that dominate ultra-deep water production. Unlike fixed platforms, which rely on rigid legs anchored solidly to the seabed, compliant towers are designed with slender, flexible steel frameworks that can sway with the motion of waves, currents, and wind without compromising their overall stability. This ability to bend and move slightly in response to environmental forces reduces the stress on the structure, making it possible to build them in deeper waters where rigid platforms would be too costly or structurally impractical. Typically, compliant towers are installed in water depths ranging from about 300 meters up to around 1,000 meters, making them well suited for areas that are beyond the reach of traditional fixed platforms, but not yet so deep that floating platforms become necessary. The engineering principle behind compliant towers relies on flexibility as a form of strength, much like the way a tall tree can sway in the wind without breaking, and this design concept allows the tower to absorb energy from waves and currents rather than resisting it entirely. The basic construction of a compliant tower involves a narrow steel lattice tower that extends from the seabed to the surface, topped by a deck that carries drilling equipment, processing facilities, and living quarters for workers. The tower itself is secured to the seabed with piles driven deep into the ocean floor, providing a firm anchor, while the flexibility of the structure allows for controlled movements. On top of the tower sits the deck, which can be as large and complex as those found on fixed platforms, with space for drilling rigs, cranes, pipelines, storage systems, and support facilities. The construction process for a compliant tower is highly complex, beginning with extensive site surveys to assess seabed conditions and environmental forces, followed by the fabrication of the steel lattice tower, often in large sections that are transported offshore and assembled on site. Heavy lift vessels are required to install the massive structural components, and precise engineering ensures that the tower is both flexible and stable once anchored to the seabed. One of the main advantages of compliant towers is their ability to provide long-term production in regions that would otherwise be inaccessible, using fixed platforms, offering a balance between cost efficiency and engineering feasibility. Because they can operate in deeper water, they opened up new offshore fields for development during the 1980s and 1990s, particularly in the Gulf of Mexico, where many compliant towers were installed. Economically, compliant towers allow oil companies to access significant reserves without the full expense of floating platforms, and they provide a reliable base for drilling and production operations that can last for decades. However, they also have limitations, as their construction costs are higher than those of shallow water platforms, and their design still restricts them to depths shallower than those where floating solutions are more practical. Maintenance of compliant towers requires constant monitoring to ensure the flexibility of the structure remains within safe limits, and the forces of hurricanes, storms, and seismic activity present ongoing risks that must be managed. From an environmental perspective, compliant towers share the same challenges as other offshore platforms, including the risk of oil spills, disruption of marine habitats, and eventual decommissioning requirements. Yet their contribution to the history of offshore engineering is undeniable, as they represent a critical step in the evolution from nearshore wooden piers and steel jackets to the advanced floating platforms that dominate modern offshore production. Compliant towers symbolize the engineering ingenuity that adapts to environmental challenges by embracing flexibility rather than rigid resistance, and their presence in offshore fields stands as a reminder of how human creativity allows energy extraction to push steadily farther into the depths of the ocean. Semi-submersible rigs are among the most versatile and widely used offshore oil platforms, and their design is based on the principle of partial submersion to achieve stability in the open sea. Unlike fixed platforms or compliant towers, semi-submersibles are not rigidly attached to the seabed, but instead float on large pontoons or columns that are ballasted with water to lower the structure deep into the ocean. By placing most of their buoyancy below the surface, these rigs reduce the impact of waves and weather on their stability, because the water beneath the surface is calmer than the surface itself. The result is a floating platform that remains steady even in rough seas, making it suitable for drilling and production in deep and ultra-deep waters where fixed platforms are not feasible. Semi-submersibles are typically anchored to the seabed with a series of mooring lines and anchors, although modern designs can also use dynamic positioning systems that employ thrusters and computer control to maintain their position without anchors. This flexibility allows semi-submersibles to be deployed in a wide range of water depths, often from a few hundred meters to several thousand meters, and they can be relocated from one drilling site to another with relative ease compared to fixed structures. The structure of a semi-submersible consists of large horizontal pontoons that provide buoyancy vertical columns that rise from the pontoons, and a wide deck platform on top that supports drilling equipment, processing facilities, storage tanks, cranes, and living quarters. Because most of the mass is below the waterline, the rig experiences less rolling and pitching, which is critical for precise drilling operations. Semi-submersibles can be used both for exploration drilling, where temporary rigs are needed to test for reserves, and for long-term production when equipped with processing facilities. Their mobility is a key advantage because companies can invest in a semi-submersible and move it to different fields as exploration and production needs change, which makes them economically efficient compared to permanent installations. Another advantage is their ability to operate in harsh environments such as the North Sea or the Gulf of Mexico, where high waves, storms, and strong winds would challenge less stable platforms. The semi-submersible design is inherently more resilient because it allows the rig to move slightly with the forces of the ocean without losing stability or safety. Constructing a semi-submersible is a major engineering achievement that involves building the massive pontoons and columns in shipyards, assembling the topside modules, and then towing the entire structure to the offshore site. Once in position, the ballast tanks are filled with water to submerge the pontoons to the correct depth, and the mooring lines or dynamic positioning systems are engaged to hold the rig steady. Life aboard a semi-submersible is similar to that on other offshore platforms, with workers living for weeks at a time in accommodation blocks that include sleeping quarters, kitchens, recreation rooms, and medical facilities. Safety systems are extensive, including lifeboats, firefighting equipment, and emergency evacuation procedures. Because the isolated location and potential risks of drilling operations require constant vigilance, semi-submersibles also face challenges, such as the need for continuous maintenance of ballast systems, mooring lines, and thrusters, as well as the logistical complexity of resupplying food, fuel, and spare parts from shore. Despite these challenges, semi-submersibles remain a cornerstone of modern offshore drilling, with dozens in operation worldwide at any given time. Their ability to balance mobility, stability, and adaptability has made them one of the most important types of offshore platforms in the history of petroleum engineering. They represent the human capacity to design structures that can endure the unpredictable power of the open sea, while enabling the steady extraction of resources from beneath the seabed. And their continued use ensures that the search for energy can extend ever farther into the world's oceans. Drill ships and floating production units represent another important category of offshore platforms, and their defining characteristic is full mobility combined with advanced systems that allow drilling and production in some of the deepest waters on Earth. A drill ship is essentially a large ocean-going vessel that has been specially designed and equipped to carry out offshore drilling operations. And unlike semi-submersibles, which are partially submerged for stability, drill ships maintain their buoyancy like conventional ships while relying on dynamic positioning systems to remain fixed above a drilling site. At the center of a drill ship is a tall derrick that houses the drilling equipment, with pipes extending through an opening in the hull known as the moon pool, which provides a direct pathway for the drill string to reach the seabed below. Dynamic positioning uses powerful thrusters controlled by satellite and computer guidance to maintain the vessel's position with extraordinary precision, even in rough seas and strong currents, without relying on anchors or mooring lines. This technology allows drill ships to operate in ultra-deep waters exceeding 3,000 meters, making them indispensable for exploring frontier regions where oil and gas reserves lie far beyond the reach of fixed or semi-submersible rigs. Drill ships are also capable of moving quickly between drilling sites, which makes them highly valuable for exploration campaigns where multiple wells must be tested over large areas of ocean. While drill ships are primarily designed for drilling, Floating production units are dedicated to the task of producing, processing, and sometimes storing hydrocarbons once a field has been confirmed and developed. Floating production units, often abbreviated as FPUs, come in various forms, including floating production storage and offloading vessels known as FPSOs, which are converted oil tankers or purpose-built ships equipped with production equipment and large storage tanks. These vessels receive oil and gas directly from subsea wells through risers and flow lines, process the hydrocarbons on board, and then either offload the oil onto shuttle tankers or send gas to pipelines for transport to shore. The advantage of FPSOs and other floating production units is their ability to operate in remote, offshore fields without the need for pipelines connected to the coast, which is particularly valuable in regions where the distance to land is too great, or the seabed conditions make pipeline installation impractical. Like drillships, FPSOs also rely on mooring systems or dynamic positioning to maintain their location above the field, and they are designed to remain on site for many years, often producing oil continuously for decades before being replaced or refurbished. Economically, drillships and floating production units represent a major investment, but their flexibility and capability to operate in ultra-deep water make them crucial for the expansion of offshore energy production into previously inaccessible areas. From an engineering perspective, they are marvels of design, combining the complexity of a drilling rig, a processing plant, and a seagoing vessel into one integrated system that must function reliably under extreme conditions. Life aboard these ships and floating units resembles life on other offshore platforms, with crews working long shifts in isolated conditions, supported by supply vessels and helicopters that deliver food, equipment, and spare parts from shore. Safety is always a central concern, with advanced firefighting systems, escape routes, lifeboats, and emergency procedures designed to address risks such as blowouts, fires, and collisions. The role of drillships and floating production units in the modern petroleum industry cannot be overstated, because they make possible the exploration and exploitation of deep water reserves that account for an ever-growing share of global oil and gas production. Their development marked a turning point in the offshore industry, opening the door to fields that lie thousands of meters beneath the ocean surface, and ensuring that offshore engineering could continue to meet the demands of global energy consumption even as shallow water reserves decline. In this sense, drillships and floating production units symbolize the next frontier of human ingenuity at sea, extending the reach of technology into the most challenging environments of the world's oceans. Tension leg platforms and spar platforms represent some of the most advanced solutions in offshore engineering, designed specifically to operate in very deep waters, where traditional fixed structures or semi-submersibles are no longer practical. A tension leg platform, often abbreviated as TLP, is a floating structure that is held in place by long vertical tendons or tethers anchored to the seabed. These tendons are kept under continuous tension, which minimizes vertical movement and provides stability while still allowing the platform to flex slightly with waves and currents. The hull of a TLP is buoyant and provides lift, while the tendons restrain it, creating a balance between upward buoyancy and downward tension. This design enables TLPs to operate in water depths ranging from 300 meters to over 1,500 meters, making them ideal for deep water oil and gas fields. The deck of a TLP, like other platforms, supports drilling rigs, production equipment, processing facilities, and living quarters, and because of their stability, TLPs can carry out both drilling and production simultaneously. One of the key advantages of tension leg platforms is their reduced heave motion compared to semi-submersibles, meaning they experience less vertical movement in rough seas, which is critical for drilling accuracy and the safety of riser systems that connect the platform to the seabed. Constructing a TLP involves building the buoyant hull and deck in shipyards, towing them to the offshore site, and then installing the tendons that anchor the structure to foundation piles or suction anchors embedded deep in the seabed. The installation requires precise engineering because the tendons must be pre-tensioned to achieve the right balance of forces. And once in place, the TLP becomes a stable yet flexible platform capable of decades of operation. Spar platforms, on the other hand, are a different type of floating platform characterized by their massive, vertical, cylindrical hulls that extend deep below the water surface, resembling a giant buoy. The spar's hull provides stability by placing most of its mass far beneath the surface, reducing the impact of waves, winds, and currents on the visible structure above. Spar platforms can be categorized into different types, such as classic spars, truss spars, and cell spars, each with variations in design to optimize weight, cost, and hydrodynamic performance. Spars are moored to the seabed using a combination of chains, cables, and anchors, and like TLPs, they can support drilling, production, and storage operations. Spar platforms are particularly well suited for ultra-deep water locations, operating in depths exceeding 2,500 meters. And they have become a popular choice in regions such as the Gulf of Mexico, where deep water fields are common. One of the engineering challenges of spar platforms is their sheer size, because the hull can extend hundreds of meters below the waterline, requiring specialized shipyards and heavy lift vessels for construction and installation. To position a spar platform, the cylindrical hull is constructed horizontally, towed to the site, and then upended by carefully ballasting with water until it stands vertically in the ocean, after which it is moored securely. Economically, both TLPs and spar platforms represent significant investments, but they enable access to reserves that would otherwise remain unreachable, making them essential for the continued expansion of offshore production into frontier areas. From a safety perspective, these platforms include advanced monitoring systems, emergency evacuation equipment, and structural redundancies to withstand extreme weather and operational stresses. From an environmental perspective, they present both opportunities and risks, as their ability to operate in deep water expands the reach of the industry, but also raises concerns about the impact of potential spills or accidents in remote and fragile ecosystems. Together, tension leg platforms and spar platforms demonstrate the pinnacle of offshore engineering, pushing the boundaries of technology to harvest energy from the deepest parts of the ocean, and they symbolize the determination of human industry to adapt and innovate in pursuit of the resources that drive modern life. Before an oil platform can ever be built at sea, a long and complex process of exploration and geological surveying must take place, because it is not enough to assume that hydrocarbons exist beneath the seabed without precise scientific evidence to guide investment and engineering. Exploration begins with regional studies that use satellite imagery, seismic data, and historical records to identify promising offshore basins where oil and gas deposits might be located. Once an area is selected, geologists and geophysicists conduct extensive seismic surveys, which involve sending controlled sound waves into the seabed and recording the reflections to create detailed images of the underground rock formations. These seismic surveys are critical because they reveal the structure of the Earth beneath the ocean, showing layers of sediment, faults, traps, and potential reservoirs that could contain hydrocarbons. The data collected is processed using advanced computer models that can simulate the likely presence of oil or gas. And only after these models confirm the probability of reserves do companies consider moving to the next stage of exploration. In addition to seismic surveys, geological sampling is often performed through core drilling, which extracts small cylinders of rock from the seabed that can be analyzed for porosity, permeability, and hydrocarbon content. These samples help scientists determine whether the rocks have the right characteristics to store and transmit oil or gas. Another important step is the use of geochemical analysis, where traces of hydrocarbons that seep naturally from the seabed are measured to provide further evidence of petroleum systems in the area. Environmental surveys are also carried out before platform construction, as engineers must understand the ocean currents, wave patterns, wind conditions, and seabed composition to design structures that can withstand the local environment. These surveys also assess the potential impact on marine ecosystems, fisheries, and coastal regions, because modern regulations require companies to demonstrate that they can minimize harm to the environment. Once exploration and surveying suggest that hydrocarbons are present, an exploratory well is drilled using a mobile drilling rig, such as a semi-submersible or drillship. This well, known as a wildcat well, is used to confirm the presence of oil or gas by directly sampling the reservoir. Drilling an exploratory well is expensive and risky because there is no guarantee that commercially viable amounts of hydrocarbons will be found, yet it remains the most definitive method of confirmation. If the well proves successful, additional appraisal wells are drilled to map the extent of the reservoir, measure pressure and temperature conditions, and estimate the total volume of recoverable resources. These appraisal wells are crucial for planning the size, type, and location of the eventual production platform. During this stage, engineers also analyze the seabed for its ability to support structures or mooring systems, as the soil composition and strength determine whether a fixed platform, a compliant tower, or a floating unit is most suitable. Surveys may reveal hard rock, soft sediments, or uneven terrain, each requiring different foundation solutions. The combination of geological, geophysical, and environmental data collected during this exploration phase forms the foundation for every engineering decision that follows, from platform design to pipeline routing. Economically, exploration is one of the riskiest parts of the offshore industry because billions of dollars can be spent without a guarantee of commercial discovery. But without this investment, no platform could ever be justified. Historically, advances in seismic technology, computer modeling, and deep water drilling have greatly improved the success rate of exploration, allowing companies to target reservoirs with higher accuracy and reduce wasted effort. The importance of geological surveys before platform construction cannot be overstated, because building a platform in the wrong location would be a catastrophic waste of resources. And the safety of the structure depends entirely on understanding the forces and conditions of the ocean environment. In essence, exploration and surveys are the invisible foundation of every oil platform, providing the knowledge and certainty required to justify the massive engineering projects that rise above the surface of the sea. The engineering design of oil platforms is a highly complex process that requires the integration of multiple disciplines to ensure safety, stability, and efficiency in one of the harshest environments on Earth. And the first consideration is always the selection of the platform type, which is determined by water depth, seabed conditions, wave height, wind intensity, current strength, and the size of the reservoir to be developed. Once the type of platform is chosen, whether it be fixed, compliant, semi-submersible, spar, or tension leg, engineers begin detailed structural modeling to simulate how the platform will respond to environmental forces over its expected lifespan. These simulations include analyses of wave loading, wind pressure, seismic activity, and the corrosive effects of seawater, because platforms must endure storms, hurricanes, and even earthquakes without structural failure. Material selection plays a critical role in the design, with high-strength steels used for legs, jackets, and decks, and reinforced concrete, sometimes chosen for gravity-based structures that rely on sheer mass to remain anchored. Every weld, joint, and fastening must be specified to withstand both static loads from equipment and dynamic loads from waves and machinery in motion. Corrosion protection is another essential design consideration, as seawater is relentlessly damaging to metals, so engineers incorporate protective coatings, cathodic protection systems, and continuous maintenance schedules into the platform's design. The layout of the topside deck is equally important because it must accommodate drilling rigs, production equipment, cranes, processing units, storage tanks, and living quarters without interfering with safety systems or daily operations. Fire safety and explosion protection drive the arrangement of equipment, with hazardous areas separated from accommodation blocks and escape routes clearly defined. Ventilation systems, blast walls, and fire suppression systems are integrated into the design to minimize the risk to human life in case of accidents. Structural redundancy is a guiding principle, meaning that critical systems are duplicated or backed up so that failure of one element does not compromise the entire platform. Stability calculations ensure that the platform will remain upright and level, even if compartments flood or equipment shifts. And in floating platforms, ballast systems and dynamic positioning thrusters are designed to maintain steady operation. Another consideration is fatigue life. Since steel structures at sea are subjected to millions of stress cycles from waves and vibrations, and engineers must design components to resist fatigue, cracking over decades of operation. Human factors are also central to engineering design, because platforms must support crews living and working at sea for weeks at a time. So living quarters, kitchens, recreation rooms, medical facilities, and communication systems are carefully planned to provide a safe and functional environment. Noise reduction, vibration control, and climate control are included to reduce stress on workers and improve efficiency. The design process also integrates logistics by ensuring that supply boats and helicopters can dock or land safely, with helipads, cranes, and storage areas positioned for efficiency. Environmental considerations shape structural design as well, since modern regulations require platforms to minimize their ecological footprint, prevent spills, and manage waste responsibly. So containment systems, flare stacks, and wastewater treatment facilities are built into the structure. The design phase is supported by advanced computer software capable of modeling ocean dynamics, simulating structural responses, and optimizing material usage. And these tools allow engineers to predict performance with remarkable accuracy before construction begins. Nevertheless, safety margins are always included because the ocean remains unpredictable. The entire design process can take years, involving engineers, geologists, naval architects, safety experts, and environmental specialists, and every detail is reviewed by regulators and classification societies before approval. In the end, the engineering design and structural considerations of oil platforms reflect the highest level of human ingenuity, balancing strength and flexibility, efficiency and safety, permanence and adaptability to create machines that stand as artificial islands in the sea, capable of producing vital energy resources while withstanding the relentless power of nature. The construction and assembly of offshore platforms is one of the most demanding tasks in modern engineering, requiring the coordination of thousands of workers, specialized facilities, and heavy equipment to create structures that will operate safely for decades in the harsh environment of the open sea. The process begins long before the platform reaches the ocean, as most of the major components are fabricated in massive onshore yards where space, tools, and skilled labor are readily available. Steel jackets, concrete bases, pontoons, and topside modules are built in sections that can weigh thousands of tons, and each section is carefully inspected for structural integrity, welding quality, and corrosion protection before moving to the next stage. In the case of fixed platforms, the jacket is often the first major element constructed, consisting of a steel lattice framework designed to be anchored into the seabed. These jackets can be taller than skyscrapers when laid on their side, and they must be transported on huge barges to the offshore site. For floating platforms such as semi-submersibles, tension leg platforms, or spars, the hull or buoyant structure is built in dry docks or shipyards, where controlled conditions allow for precise assembly and installation of ballast tanks, columns, and pontoons. Once these massive components are complete, they are towed out to sea using powerful tugboats, often traveling at only a few knots because of their immense size and weight. The offshore installation process is a carefully planned operation that depends on calm weather, because high waves or strong winds can make positioning dangerous or impossible. Heavy lift vessels, sometimes capable of lifting more than 10,000 tons in a single operation, are used to place topside modules onto the supporting structure. These modules include drilling rigs, processing equipment, power generation units, cranes, and living quarters, and they are often pre-assembled on shore to reduce the amount of work required at sea. The precision needed for these lifts is extraordinary, as modules must align perfectly with connection points while suspended above the ocean, and teams of engineers and divers ensure proper fit and secure attachment. For tension leg platforms, once the floating hull is in position, massive tendons are lowered to the seabed and connected to anchors, after which the hull is ballasted to apply constant tension. For spar platforms, the cylindrical hull is towed horizontally to the site and then upended by carefully flooding ballast tanks until it stands vertically in the water, after which it is moored with chains and cables. Once the primary structure is installed, miles of pipelines and risers are connected to carry oil and gas from subsea wells to the platform and eventually to shore. Electrical and communication systems are installed to link every part of the platform, while safety systems such as fire suppression, gas detection, and emergency evacuation equipment are tested. Living quarters are furnished with kitchens, recreation rooms, medical facilities, and sleeping areas, ensuring that crews can live on board for weeks at a time. The final stage of assembly involves extensive commissioning, during which every piece of equipment is tested under simulated operating conditions to confirm functionality, safety, and reliability. Only after passing this rigorous process can the platform begin drilling or production. The construction and assembly process often takes several years, from the initial cutting of steel to the moment the first barrel of oil is produced, and the cost can reach billions of dollars, depending on the size, depth, and complexity of the project. Yet despite the enormous scale of these efforts, platforms are expected to operate continuously for 20 to 30 years, with only periodic shutdowns for maintenance and upgrades. This long-term reliability is only possible because of the precision, planning, and discipline applied during construction and assembly. Offshore platforms are therefore not only feats of design, but also monuments to industrial organization, where the combined effort of thousands of individuals results in structures that rise out of the sea like artificial islands, built to withstand storms, corrosion, and the relentless forces of the ocean, while providing the energy that powers modern civilization. Transporting and installing oil platforms at sea is an operation of extraordinary scale and precision, because the structures involved are often among the largest objects ever built by humans, and moving them from fabrication yards to their final offshore locations requires careful planning, specialized vessels, and favorable weather conditions. Once a platform or its major components are completed on shore, they must be loaded onto huge barges or heavy transport ships designed to carry weights of tens of thousands of tons. These transport vessels are equipped with ballasting systems that allow them to submerge partially so that the platform sections can be floated into position and then secured for the journey. The transportation itself is conducted at very low speeds, often just a few knots, because the size and weight of the cargo demand extreme caution. And during the voyage, teams of engineers and navigators monitor stability, weather, and sea conditions continuously to ensure safety. Tugboats often accompany the transport to provide additional control and maneuverability, especially when entering or leaving harbors or approaching the offshore site. Once the platform or module arrives, the process of installation begins, and this stage is highly dependent on the type of platform being deployed. For fixed platforms, the first step is to lower the steel jacket or concrete base to the seabed using heavy lift vessels or controlled ballasting. Divers and remotely operated vehicles assist in positioning the jacket accurately on the ocean floor, after which long steel piles are driven deep into the seabed using hydraulic hammers to secure the structure in place. Once anchored, the topside modules are lifted by crane ships, some of which are capable of handling lifts exceeding 10,000 tons, and these modules are carefully aligned and bolted to the jacket structure. For floating platforms such as semi-submersibles or spar platforms, installation involves towing the buoyant hull into position and then using ballasting systems to lower it into its operational draft. In the case of spar platforms, the massive cylindrical hulls are floated horizontally and then upended by filling ballast tanks with water until they stand vertically, a maneuver that requires extraordinary precision and stability control. Tension leg platforms have an even more specialized installation process, as once the hull is floated into place, enormous steel tendons are connected between the platform and seabed anchors, and the platform is ballasted to create constant tension in the tendons that stabilizes the structure. Drillships and floating production units, by contrast, use dynamic positioning systems or mooring lines to maintain their position, and their installation is primarily focused on connecting subsea equipment, risers, and flow lines. After the platform is positioned, the next critical stage is the connection of subsea wells and pipelines. Flexible risers, rigid pipes, and umbilicals carrying power and control signals are installed using remotely operated vehicles and specialized laying vessels, and these connections ensure that hydrocarbons can flow from the reservoir to the platform for processing. Simultaneously, safety systems such as blowout preventers, emergency shut-off valves, and monitoring equipment are tested to confirm readiness. The installation process also includes the setup of logistical systems, such as helicopter landing pads, supply boat docking arrangements, and communication links to shore bases, ensuring that crews can be supported once operations begin. The entire transportation and installation phase is subject to strict safety regulations because any mistake could result in catastrophic damage to equipment, loss of life, or environmental disaster. Weather windows are carefully chosen to minimize risks, and operations are often delayed if high waves, storms, or strong currents are predicted. Even after installation is complete, weeks or months of commissioning are required to test every system and certify the platform for production. Economically, the transportation and installation stage represents a significant portion of total project cost. But it is also the most visible moment when the platform transitions from an abstract engineering design to a functioning offshore facility. Watching a platform being transported and installed is a demonstration of human capability, as objects larger than skyscrapers are carefully moved across oceans and placed with millimeter accuracy onto the seabed. This stage of offshore development combines naval engineering, structural engineering, marine operations, and logistics into a single seamless process that ensures platforms are ready to begin the critical task of extracting energy from beneath the ocean floor. Drilling operations and the oil extraction process on platforms form the very core of their existence, because all of the massive structures, the engineering design, and the logistical efforts ultimately serve the single purpose of reaching hydrocarbon reservoirs beneath the seabed and bringing those resources safely to the surface. The drilling process begins with positioning the rig directly above the intended well location, which may already have been identified during geological surveys and exploratory drilling. Once the rig is stabilized, drilling engineers assemble a drill string consisting of drill pipes connected end to end with a heavy drill bit at the bottom. The drill bit is rotated by surface equipment or by downhole motors, and as it cuts through layers of rock, drilling mud is pumped down the drill string and circulated back up to the surface. This mud is not simply water, but a specially formulated fluid designed to cool the drill bit, carry rock cuttings to the surface, maintain pressure balance, and stabilize the borehole walls. The circulation of drilling mud is critical because it prevents blowouts, which are sudden and dangerous releases of oil or gas from high-pressure formations. As drilling progresses, steel casings are lowered into the hole and cemented in place to line the wellbore, ensuring stability and preventing fluids from migrating between different rock layers. Drilling is often performed in stages, with each stage involving drilling to a certain depth, installing casing, and then continuing deeper until the reservoir is reached. Once the well penetrates the reservoir, additional safety equipment, such as blowout preventers, is installed at the wellhead to provide control in case of unexpected pressure surges. The actual extraction of oil begins with perforating the casing in the reservoir zone, allowing hydrocarbons to flow into the wellbore. In many cases, the natural pressure of the reservoir is enough to push oil and gas to the surface. But as production continues and pressure declines, artificial lift methods such as pumps, gas injection, or water flooding may be used to maintain output. On the platform's deck, the produced fluids, which include oil, gas, and water, are processed in separation units that divide them into their individual components. Gas may be compressed and sent via pipelines to shore, re-injected into the reservoir to maintain pressure, or used to power the platform itself. Oil is stabilized, sometimes stored temporarily on the platform, and then transported either by pipeline or shuttle tanker. Water is treated and often re-injected into the reservoir or discharged according to environmental regulations. Drilling and production operations require constant monitoring from control rooms staffed with engineers who track pressures, flow rates, and equipment status in real time. Any anomalies can trigger alarms and immediate responses to prevent accidents. Drilling operations are not limited to a single well, as most platforms drill and complete multiple wells connected to a network of subsea systems, increasing the efficiency of the field. Directional drilling is frequently used, allowing wells to be drilled at angles or even horizontally to reach different parts of the reservoir from a single platform. This technique maximizes production while minimizing the number of surface structures. The complexity of drilling operations also requires extensive maintenance and periodic workovers, which are interventions carried out to repair or stimulate wells that are producing less efficiently. These workovers may involve cleaning out the wellbore, replacing tubing, or applying chemical treatments. Safety is always at the forefront, because drilling and extraction involve high pressures, flammable hydrocarbons, and heavy equipment, all of which pose risks if not controlled properly. Emergency systems, regular drills, and strict operational procedures are in place to protect workers and the environment. The entire drilling and extraction process reflects the balance of science, engineering, and careful human oversight, transforming hidden geological formations beneath the ocean into accessible resources that power industries and households around the world. Ultimately, drilling operations and oil extraction on platforms are not just mechanical tasks, but highly coordinated efforts that embody the essence of offshore engineering, combining precision, safety, and innovation to sustain the flow of energy from the depths of the earth to the surface of the sea. Safety systems and risk management on oil platforms are of the highest importance because these structures operate in remote, isolated, and often hostile environments where any incident can have catastrophic consequences for human life, equipment, and the surrounding ecosystem. Every platform is designed and operated with multiple layers of safety systems intended to prevent accidents, mitigate risks, and ensure rapid response if something goes wrong. The most fundamental system is the blowout preventer, a large and powerful set of valves installed at the wellhead that can seal the well in case of uncontrolled pressure surges from the reservoir. Blowout preventers are capable of closing around the drill pipe or even cutting it completely to shut the well, and they represent the last line of defense against blowouts that could otherwise lead to explosions or oil spills. Fire protection is another critical aspect, as oil and gas are highly flammable. Platforms are equipped with fire detection systems, automatic sprinkler systems, foam suppression systems, and strategically placed fire extinguishers, all linked to alarms and control rooms. In case of a fire, blast walls and fireproof barriers are designed to contain flames and protect vital areas such as living quarters. Gas detection systems continuously monitor the atmosphere for leaks of hydrocarbons or toxic gases, and if dangerous concentrations are detected, alarms sound and automatic shutdowns may be triggered. Risk management also involves structural safety, with platforms built to withstand extreme storms, high waves, and in some regions, even earthquakes. Redundancy is a key principle, meaning that critical systems such as power generation, pumps, and communication links have backups so that operations can continue even if one system fails. Safety also extends to evacuation procedures. Every platform has lifeboats, life rafts, and personal flotation devices for all workers, with lifeboats designed to be launched quickly, even in rough seas. Helicopter evacuation pads provide another escape route, and regular drills ensure that workers know how to respond in emergencies. The human element of safety is managed through strict training and certification requirements, with workers trained in firefighting, first aid, survival at sea, and emergency evacuation. Crew rotations are carefully planned to prevent fatigue, which is a major contributor to accidents, and safety briefings are a routine part of offshore life. Risk management also covers environmental safety, as platforms must be prepared to handle spills and leaks. Oil spill response equipment, containment booms, and dispersants are kept on hand, and response teams are trained to deploy them immediately in case of a release. Platforms are required to have detailed contingency plans approved by regulators that outline how they would respond to various scenarios, from minor leaks to major disasters. Regular safety audits and inspections are carried out both by the operating company and by external authorities to ensure compliance with international standards. Advanced monitoring systems track vibrations, pressures, and structural integrity in real time, giving engineers early warning of potential failures. Maintenance schedules are strictly enforced to keep equipment in good condition, and any signs of wear or corrosion are addressed immediately. Culturally, safety is emphasized as a shared responsibility, with all workers encouraged to report hazards and stop work if they feel unsafe. Economically, the importance of safety systems and risk management cannot be overstated, because accidents not only endanger lives and the environment, but also result in enormous financial losses, reputational damage, and legal consequences. The offshore industry has learned painful lessons from past disasters, such as blowouts and oil spills, and modern platforms reflect decades of improvements aimed at preventing similar tragedies. Ultimately, safety systems and risk management define the integrity of oil platforms, ensuring that the pursuit of energy resources is balanced with the protection of workers, the preservation of the environment, and the responsibility to operate with the highest possible standards of engineering and human discipline. The environmental impact of offshore drilling and oil platforms has long been a subject of concern, because the process of extracting hydrocarbons from beneath the seabed inevitably carries risks to marine ecosystems, coastal environments, and the global climate. One of the most visible risks is the possibility of oil spills, which can occur during drilling, production, transportation, or accidents. When oil is released into the ocean, it spreads across the surface and forms slicks that harm marine life by coating birds, fish, and mammals, reducing their ability to breathe, insulate, or move effectively. Oil spills also damage coastal ecosystems such as mangroves, salt marshes, and coral reefs, and cleanup is often slow, difficult, and incomplete. Even in the absence of major accidents, routine operations on platforms produce discharges of drilling muds, produced water, and chemical additives that must be carefully managed to avoid contamination. Noise from drilling operations and seismic surveys also impacts marine animals, particularly whales and dolphins, that rely on echolocation, as the intense sound waves can disrupt communication, navigation, and feeding patterns. The physical presence of platforms alters marine habitats by introducing artificial structures into the ocean, which sometimes serve as artificial reefs, but can also disrupt natural ecological balances. Air pollution is another significant impact, as platforms release greenhouse gases such as carbon dioxide and methane, along with other emissions from power generation, flaring, and transportation. These emissions contribute to climate change and regional air quality problems. Despite these challenges, significant mitigation efforts have been developed over decades to reduce environmental harm. Modern platforms are required to comply with strict environmental regulations that govern waste disposal, emissions, and spill prevention. Blowout preventers, double hulls on transport tankers, and improved well-control technologies are designed to minimize the risk of catastrophic releases. Produced water is treated before discharge to remove oil and contaminants, while drilling muds are increasingly formulated with environmentally friendly components. Seismic surveys are sometimes modified with soft start procedures or exclusion zones to reduce harm to marine mammals, and monitoring programs are often required to track the health of local ecosystems near drilling sites. Companies also invest in spill response capabilities, maintaining equipment such as booms, skimmers, and dispersants at the ready, along with trained crews to respond quickly if an incident occurs. International frameworks such as MARPOL, OSPAR, and national environmental protection laws set standards that platforms must meet, and inspections ensure compliance. Some platforms are designed with zero discharge systems in sensitive areas, meaning that all waste is collected and transported to shore rather than released into the ocean. Advances in drilling technology, including directional drilling and subsea completions, have also reduced the footprint of offshore operations by allowing multiple wells to be drilled from a single platform, limiting the number of structures in the ocean. Beyond mitigation during active operations, decommissioning practices are evolving to ensure that platforms are removed or repurposed in environmentally responsible ways, with some structures converted into artificial reefs through programs that benefit marine biodiversity. Economically, the cost of environmental protection is justified not only by regulatory compliance, but also by the potential damage that accidents can cause to a company's reputation and long-term viability. Public awareness and activism have increased pressure on the industry to operate more sustainably, and many companies now include environmental stewardship as part of their corporate policies. While offshore drilling will always involve some degree of environmental impact, the combination of engineering advances, regulatory frameworks, and industry practices continues to reduce risks and improve safety. Ultimately, the environmental impact of offshore drilling and mitigation efforts reflects the broader challenge of balancing the world's demand for energy with the responsibility to protect the oceans, demonstrating that technological progress and careful management can coexist with environmental awareness even in the most demanding industrial activities at sea. The economic importance of oil platforms and their role in global trade is immense, because they provide access to resources that fuel nearly every sector of modern life, from transportation and manufacturing to electricity generation and consumer goods. Offshore oil accounts for a significant portion of the world's petroleum supply, and without oil platforms, many countries would lack the energy security needed to support their economies. The construction, operation, and maintenance of platforms require billions of dollars in investment, and these expenditures generate entire industries of shipyards, steel manufacturers, engineering firms, logistics providers, and service companies. Each platform creates thousands of direct and indirect jobs, ranging from welders and engineers to helicopter pilots and supply chain managers, and the ripple effect extends to coastal communities that host support bases and fabrication yards. The output of platforms also directly supports national economies, because oil and gas are key drivers of trade balances, government revenues, and foreign exchange reserves. Countries with offshore reserves can export surplus production, influencing global energy markets and geopolitics, while import-dependent nations rely on steady flows of crude oil and liquefied natural gas to sustain industry and consumer demand. Oil prices, which are influenced by offshore production levels, affect inflation, transportation costs, and the prices of countless goods. A disruption in offshore production due to accidents, political instability, or natural disasters can have immediate effects on global trade, causing price spikes and supply chain challenges. Platforms also represent strategic assets in international relations, as control over offshore fields can strengthen national security and create leverage in diplomatic negotiations. Global shipping lanes are intertwined with offshore production because tankers and pipeline systems transport oil and gas from platforms to refineries and then onto markets across continents. Floating production storage and offloading units in particular serve as critical nodes in this network, allowing continuous production in remote regions without fixed pipelines. Economically, the presence of oil platforms can transform local economies, bringing investment, infrastructure, and development. But they can also create dependency on resource revenues, making economies vulnerable to fluctuations in oil prices. Governments often impose taxes, royalties, and profit-sharing agreements on offshore production, which can amount to billions in public revenues used to fund schools, hospitals, and infrastructure projects. In regions such as the North Sea, the Gulf of Mexico, and offshore Brazil, entire national economies have been shaped by the presence of offshore oil, with industries and policies built around sustaining production. The financial stakes are so high that companies and governments continuously invest in technology to extend the life of fields, increase recovery rates, and push exploration into ever deeper waters. At the same time, oil platforms play a controversial role in the transition to renewable energy, because while they remain essential to the global economy, they also represent the continued dependence on fossil fuels. Some argue that revenues from offshore oil should be invested into developing cleaner energy alternatives, while others emphasize that petroleum will remain indispensable for decades due to its role in petrochemicals, aviation, shipping, and heavy industry. The global trade system reflects this duality, with oil platforms standing as both symbols of economic power and reminders of the challenges of energy transition. Insurance markets, financial institutions, and commodity traders all depend on the steady operation of platforms, and their productivity influences stock markets, national budgets, and international agreements. From a broader perspective, oil platforms embody globalization because they connect remote ocean basins with the daily energy needs of billions of people on land. The crude oil extracted from a platform in the Gulf of Mexico may end up fueling cars in Europe, powering factories in Asia, or being refined into plastics in Africa. The chain of value begins with the platform and extends through every aspect of global trade, making offshore structures one of the most important economic engines of the modern world. The future of oil platforms is shaped by three interconnected themes: the need for responsible decommissioning of aging structures, the opportunities for recycling and repurposing materials and facilities, and the exploration of alternatives as the world gradually transitions toward new forms of energy. Decommissioning is the process of safely retiring platforms at the end of their productive life, which typically spans 20 to 40 years, depending on reservoir size, economic conditions, and maintenance. Once production declines to the point where operating costs exceed revenues, companies must begin planning for removal, and this involves sealing wells permanently, disconnecting pipelines, dismantling topsides, and either removing or repurposing the supporting structures. The sealing of wells is a critical step because it prevents hydrocarbons from leaking into the ocean, and it is achieved by filling the well bore with cement and ensuring that casings remain intact for the long term. Removing topside equipment requires heavy lift vessels, similar to those used during installation, and each module is transported back to shore for dismantling, recycling, or disposal. Jackets, spars, or hulls can either be removed entirely or, in some cases, cut down to a safe depth below the waterline and left in place as artificial reefs, a practice known as rigs to reefs, which has been adopted in regions such as the Gulf of Mexico to promote marine biodiversity. Recycling plays a major role in decommissioning because much of the steel, copper, and other materials used in platforms can be reclaimed and reused in new industrial projects, reducing waste and creating economic value from structures that would otherwise be discarded. However, the process is costly, and decommissioning has become one of the largest liabilities facing oil companies, often requiring billions of dollars in spending and years of work for a single platform. Regulators enforce strict rules to ensure environmental protection, and international standards govern how decommissioning must be carried out, with safety and sustainability as top priorities. At the same time, alternatives are emerging that reflect broader shifts in global energy systems. Some decommissioned platforms are being repurposed for scientific research, aquaculture, or renewable energy production, serving as bases for offshore wind farms or wave energy converters. Engineers have studied ways to use existing offshore infrastructure to support carbon capture and storage by injecting carbon dioxide into depleted reservoirs, turning platforms into tools for climate mitigation rather than fossil fuel extraction. In parallel, the offshore industry is increasingly investing in renewable energy technologies, with offshore wind turbines already widespread in Europe and Asia, and floating wind farms beginning to demonstrate the potential of deep-water renewable generation. Oil platforms themselves may provide lessons and transferable technologies for these new industries, as the expertise in building stable offshore structures, managing power systems at sea, and maintaining equipment in hostile environments applies directly to renewable projects. Economically, the future of oil platforms depends on balancing continued demand for oil and gas with the growing push for decarbonization. While petroleum will remain vital for decades due to its role in transportation, petrochemicals, and industry, the long-term trajectory points toward diversification, with companies repositioning themselves as broader energy providers rather than solely oil producers. This transition creates both challenges and opportunities for offshore engineering, as the vast knowledge accumulated in designing, constructing, and operating platforms can be redirected toward new frontiers. From an environmental perspective, the future of platforms must address not only decommissioning and recycling, but also stricter standards for minimizing emissions, protecting ecosystems, and ensuring that the mistakes of past decades are not repeated. In essence, the story of oil platforms is moving into a new chapter, where the giant structures that once symbolized industrial power and energy security may increasingly symbolize adaptation, sustainability, and innovation. Whether dismantled, recycled, repurposed, or replaced by renewable technologies, oil platforms will continue to influence the global energy landscape, reminding us of both the achievements and the responsibilities that come with harnessing the resources of the ocean.